Hey, welcome to another installment of Annoying Calculations and Statistics. And we'd like to talk about the correlation coefficient for two random variables. So we'll go ahead and share screen here and let's see if there we go. And what I'd like to show is that the correlation coefficient, which is defined to be the covariance of two random variables divided by the product of their respective standard deviations, is always between 1 and -1. And of course, I should, the assumption here, and pedantic enough to say it, that mu1, mu2, sigma 1, sigma 2 all exist and are finite. And yes, there are some distributions where that's not the case. Okay, so let's get started here. And so the way we do this is, first of all, let's start off, and well, I should remind you of a couple of things. Remember that the covariance of two random variables is defined to be the expectation of the difference between y1 minus mu1, y2 minus mu2. You take the expectation and of the product of these two things, and that's what the covariance of these are. Now let's go ahead and get started on the general result. And the way you do this, the proof of this is extremely similar to the proof of the Cauchy-Schwarz. Inequality. It's similar to the proof of the Cauchy-Schwarz inequality. And basically what that basically says there, it says that if you take the inner product of vector v1, vector v2, and you divide that by the norm of v1 times the norm of v2, that what you get will always be between 1 and -1, assuming that v1 is not the zero vector of v2. And that's, and if you're familiar with dot product from calculus 3, that's how we remember, that's how you define the cosine of the angle between two vectors. Well, all of this is going to, the technique you use to prove that is going to be basically the technique you use to prove this. And so let's go ahead and get started. So let's start off. So here's the start of the proof. Start off by taking the expectation, and I'm going to do something a little strange here. I'm going to take the expectation of t y1 minus mu 1 plus, and then I'm going to go ahead and do this, plus y2 minus mu 2. And I'm going to look at this squared. Now, because you're taking the expectation of something that's guaranteed to be no less than 0, something 0 or something non-negative, you know for a fact that's going to be greater than or equal to 0 for all t. Now that's going to be important. T is just some scalar variable. So now we're going to start using the linearity of the expectation operator all over the place. You square this, so this will be t squared, y1 minus mu1 squared, plus 2t, y1 minus mu1, y2 minus mu2, plus y2 minus mu2 squared. And that's going to be greater than or equal to 0 for all t, just like before. Now remember, the expectation is really a linear operator. So I'm going to use linearity to write the fact that you can pull the scalar out. You now have this, right? Then you can pull this 2t out. Now you have the expectation of y1 minus mu1, y2 minus mu2, plus, and I should bracket these, and plus the expectation of y2 minus mu2 squared. And remember, that's greater than or equal to 0. Now here is where things get fun. What I'm going to do is this is going to be a real number. I'm going to call this real number A. By B, I'm going to set that equal to 2, expectation of y1 minus mu1, y2 minus mu2, which is a covariance, of course. So that's what's going to be, that's going to be B. And by C, I want to call that the expectation of y2 minus mu2 squared. And I better erase, oh no, that's a minus, you can tell. And notice that A, the coefficient, is going to be the variance of y1. C is going to be the variance of y2. And notice this middle coefficient is double the covariance. So now we have a polynomial, a t squared plus b t plus c, that's what this is, which is greater than 0 for all t. Now, this is a polynomial, right? So what this means is, by the quadratic formula, the discriminant, and just remind you of the quadratic formula, if you have ax, a squared t squared plus bt plus c, roots are t equals minus b plus or minus. I should remind you of that. And this, of course, is called the discriminant. And this polynomial is greater than or equal to 0 for all t. So what that means is that you cannot, this part right here has to be imaginary or 0. So because this has, it can be 0 once. I mean, it can actually be 0, or you can have imaginary roots. This means that b squared minus 4ac has to be less than or equal to 0, or else you would have 2 real roots. We know this polynomial, however, is always greater than or equal to 0. So that's just basic quadratic formula. Now let's take a look at what we have here. B squared is this. So substituting back for b squared, we have 2 expectation of y1 minus mu1, y2 minus mu2. So I'll close that up. Squared minus 4 times the expectation of y1 minus mu1 squared, expectation of y2 minus mu2 squared. All right, is less than or equal to 0. So now we're almost done, because this part, this is a square here. You just move this to the other side. You square this, so you have 4. This part right here is now the covariance. but it's squared, is less than or equal to 4. This part right here is just the variance of y1. This is just the variance of y2. So that must be true. Then dividing by 4, we get the square of the covariance divided by, and you don't have to worry about division since these are all positive, is less than or equal to 1. And it follows that covariance y1, y2, sigma 1, sigma 2 is less than or equal to 1, greater than or equal to -1. And of course, this assumes this is not non-zero variance, which it would be silly to calculate covariance if we had zero variance to begin with. So this, of course, is our correlation coefficient. Oops, it's a little bit, there's a row. And that's what we set out to do. So thanks for watching, and I'll do another one of these soon.